and I'm going to be talking to you guys today about organic chemistry. Organic chemistry is the study of carbon-containing compounds. History of organic chemistry. So it was believed that organic compounds could only be obtained from living organisms such as plants, animals, humans, things like that. But in 1828, Frederick Wohler proved the vital force theory wrong by synthetically producing urea. Then, Frederick August Kekulé von Stradonce discovered the benzene ring. So the combination of these two people, as well as Justus von Liebig, brought to arise organic chemistry. A little bit of the history of organic chemistry. Let's take a look at what organic chemistry is all about. So we talked about how it is the study of carbon-containing compounds. Let's take a look at what carbon is all about. So carbon atoms are unique because they are the only element that can bond to itself. Not only can carbon bond to itself, but it can also combine with a large variety of other elements. Some examples can include carbon, hydrogen, oxygen, and nitrogen. In addition, there are more than 1 million carbon compounds that have been discovered, and there are new compounds that are constantly being artificially / synthetically made. Taking a look at the structure of carbon compounds. So carbon can only have 4 bonds. So you have a tetrahedral, which is 4 single bonds and an sp3 hybridization. Next, you have a trigonal planar, which is 2 single bonds and 1 double bond. And lastly, you have a linear structure, which is 1 single bond and 1 triple bond. And as you see, you have 4 single bonds, 2 single, 1 double, which is 4, and then a single and a triple, which is also 4. Let's go over some definitions that are going to help us better understand organic chemistry. So let's talk about solubility and polarity. So when something is polar, that means it occurs when there is an electronegativity difference between the bottom atoms. When something is nonpolar, it occurs when electrons are shared equally between atoms of a diatomic molecule or when polar bonds in a larger molecule cancel each other out. Now let's talk about solubility. So when something is soluble, it can dissolve in a solvent. When something is insoluble, it cannot dissolve in a solvent. Look at the most common carbon bonds. So you have carbon to hydrogen and carbon to carbon. And here our definitions come into play: nonpolar and insoluble. So carbon to hydrogen bonds are called hydrocarbon bonds. These hydrocarbon bonds have 4 functional groups. So functional groups we will go over a little bit later to help us better understand. So we have alkanes, alkenes, alkynes, and aromatic hydrocarbons. Different groups, we have something called functional groups. So these are specific groupings of atoms within molecules that have their own characteristic properties. This is regardless of the other atoms that are present in the molecule. Common examples include alcohols, amines, carboxylic acid, ketones, and ethers. So as you can see, you have root words here. Alkene is E-N-E, alkyne is Y-N-E, haloalkane is I-D-E, and amines are amines. Organic chemistry, the structure and characteristics of carbon molecules and functional groups. Let's take a look at other parts of organic chemistry. So we have amino acids, carbohydrates, lipids, and nucleic acids. Over the structure of proteins. So we have 4 different structures. So we have the primary structures, which are the amino acid sequences within the polypeptide chain. Next, we have secondary structures, which is what gives the protein its structure and does so through the interaction between atoms. So as you can see here, we use our pen, we have B-pleated sheets and we have an alpha helix. So in the next step, these here are local foldings of the polypeptide chains into helices or sheets. So next, as you see, we have the tertiary structures that are the intermolecular forces between the atoms that give it the structure. So the B-pleated sheet here, let's use our pen here, and then the alpha helix, or helices, fold together to form a three-dimensional folding pattern of a protein. So lastly, we have the quaternary structure, which is the combination of multiple portions of proteins, which all together give the protein their structure here. And because they are folded together, this gives a more balanced structure here. Of proteins, let's take a look at how we can classify proteins. So one way to classify proteins is through their shape. So we have globular proteins and we have fibrous proteins. So an example of a globular protein would be myoglobulin. So as you can see here, myoglobulin isn't a perfectly spherical shape or globe-like, but it's very close to that. Next, we have a fibrous protein, and a great example of that would be collagen here, and as you can see, they are in long strands just like fiber. Of organic chemistry, all about carbon and different types of proteins and way to classify them. Let's take a look at carbohydrates. So there's different classes of carbohydrates. We have monosaccharides, which the root word there, mono, means one, disaccharides, root word there means two, and polysaccharides, where poly means many. So the name carbohydrate comes from the empirical formula for sugars. So let's go back to monosaccharides. The most common type of monosaccharides are glucose and fructose. Next, let's take a look at disaccharides, which is a more complex carbohydrate, and which includes sucrose and lactose. Most commonly, disaccharides are referred to as sugars. Next, we have polysaccharides, which is your most complex type of carbohydrate. And polysaccharides include starch, glycogen, and cellulose. Now, carbohydrates. Let's take a look at lipids. So, as previously mentioned with our vocabulary words, lipids are nonpolar and soluble. There are two different classes of lipids. We have saturated and we have unsaturated fats. So there are healthy and unhealthy types of fats, otherwise known as saturated and unsaturated fats. So saturated fats are known as your bad fats and include oils such as stick margarine and vegetable oil. Saturated fats are typically used in fast food, and here in the South, saturated fats are our typical preferred cooking method. Saturated fats can cause high cholesterol, cardiovascular disease, and even contribute to obesity. In contrast, we have unsaturated fats, which are our healthy fats, which include safflower oil, sesame oil, avocado oil, anything nut or plant-based. So these are typically not used because they are the more expensive type of fat, and people prefer to use something cheaper than something more expensive, even if it has adverse health effects. Here at what makes lipids nonpolar and insoluble. So lipids have what we call a phospholipid bilayer. So in the phospholipid bilayer, each of the phospholipid molecules have a hydrophilic or polar head and a hydrophobic nonpolar fatty acid tail. So hydrophilic means water loving and hydrophobic means water hating. So the tails are placed inside towards each other and the heads are on the outside. So if you've ever tried to mix water and oil, you've noticed how the oil separates from the water. So those hydrophobic tails make the oil collect towards each other while pushing the water out, which is why you see that separation in water and oil. Let's take a look at nucleic acids. So we have two different types of nucleic acids. We have DNA and we have RNA. So DNA is otherwise known as deoxyribonucleic acid. DNA is a double-stranded sugar binding to a phosphate. And as you can see here, DNA has cytosine, guanine, and adenine, but it also has thymine as its base pair here. So now that we've talked about DNA here, let's take a look at RNA. So RNA is otherwise known as ribonucleic acid. So ribonucleic acid is usually a single-stranded sugar binded to a phosphate, which includes ribose there. So as you can see, it is single-stranded here. The difference between RNA and DNA is RNA has uracil rather than thymine, but RNA also includes cytosine, guanine, and adenine. So the reason RNA has uracil and DNA has thymine is, according to the National Science Teaching Association, RNA uses uracil because it is shorter lived than DNA and it can get by with energetically cheaper uracil. Learned what organic chemistry is all about. Let's take a look at some recent organic chemistry discoveries. So here I have 5 new ones that have been discovered. So there's a new macrolactone database that could aid in drug discovery research. CRISPR, which is helpful in many ways, has actually been able to help identify potential Alzheimer's related proteins. There is a new biosensor for the COVID-19 virus, which is really big right now. Hopefully that helps out with a lot of things. There is a new way how water could replace toxins and be able to help us store and make plastics more economically. And lastly, we have how diamonds could help in an energy storage solution. Now that we've talked about some of the recent organic chemistry discoveries, let's take a look at some people that are playing and have played big roles in new discoveries in organic chemistry, as well as laying foundations for older organic chemistry fundamentals. People who are helping us to make these recent organic chemistry studies. So George Olah is a giant in the field of physical/organic chemistry and the study of reactive intermediates. So he has been able to develop superaids and study carbocations and essentially end the debate about the existence of non-classical ions. He has also been celebrated for his work in organofluorine chemistry and organic synthesis. In addition, Emil Fischer is a German scientist who is responsible for developing many fundamental synthetic methods, including the Fischer aldol synthesis, the Fischer oxazole synthesis, and Fischer esterification. He laid the basis for the entire field based off of carbohydrate chemistry, and his proof of the structure of glucose was a tour de force, and don't forget about his Fischer projections, which was, by the way, a lucky guess. So essentially, he gave life to chemistry as the compounds he worked with literally drove him insane. Today on organic chemistry, we've gone over how organic chemistry is the study of carbon-containing molecules, how organic chemistry was discovered in the 19th century, how carbon is structured, how proteins are structured, different type of carbohydrates, lipids, which is your saturated and unsaturated, and then carbs, which is your monosaccharide, disaccharides, and polysaccharides, and then nucleic acids, which is our DNA and RNA, in addition to how new discoveries are constantly being made in the organic chemistry field. The encyclopedia for my definitions. I use NSTA.org, which is the National Science Teaching Association, for my commentary on uracil, and then I used our chemistry book for the majority of my information in my PowerPoint.